We're at 2.6 now. Chapter 2 in and of itself, as you guys can see, I mean, a lot of it's review. You know, graphing lines, linear functions, what is a function, types of functions, circles. And we're kind of maintaining the same trend with it. Not until like chapter 3 or 4 do we get into a lot of newer things. But today, we're going to recognize basic functions, which are all these graphs behind this board, apply vertical, horizontal translations, apply reflections across the x and y axes, and then summarize transformations of graphs. Okay, and what I mean by that is I'm going to give you a problem where, okay, we're going to put all of this stuff together. And then what kind of order should we do that in so that we don't make any mistakes? So the warm-up, actually, I'm just right here. So looking at the warm-up here, these are transformations that are happening to these graphs. So for part A, what's happening to the graph? What transformation is occurring? Horizontal one, right? And it's going to go to the right 3. What type of transformation is this guy? Reflection? Yep. X or Y? X-axis. And then what about this guy? Vertical shift, right? Went down 2. Very good. Perfect. So you're retaining some knowledge from Algebra 2. That's good. So let's look at these 9 graphs. These are our basic functions. We call them the parent functions because that's where we all start before we start moving things around, right? Okay, that's the key part. The first one's a linear function. That's our y equals mx plus b. So we've done those too many times. Constant functions. So that's just our horizontal line. So b is just any constant that we can have. So 4, 5, -5, 1,000, whatever it is. 3 is the identity function. Okay, so this is the same thing as me writing y equals x. Okay. Now the reason why it's called the identity function is, well, think about it. If I plug 1 in for x, my y is also going to be 1, right? It keeps its identity. It doesn't change the number. I could plug 2 into here, and the answer is going to be 2, 3, 3, and so forth. Okay. For a quadratic function, that's our x squared. Cubic, okay, that's the 3rd power. So it has like this little saddle thing going on here where it's, you know, the changes are very minute before it starts picking back up again. 6 is a square root function, and it's just an arc, okay? Now, this arc doesn't level off. It does keep increasing, but those changes are so minute that it's hard to tell, so sometimes you can zoom in on the graph to see those. Number 7, a cubic root function. Again, I like this. This is pretty cool, just kind of how the design is with it. 8's our absolute value. And then 9's a reciprocal function. You know in mathematics, reciprocal means you're taking like 1 over something, okay? Now, this graph's pretty interesting because here's the deal. Is it ever going to hit the x-axis with how it's graphed? No, right? Okay. If it did hit the x-axis, that means y is 0. Is there any number I could plug into here where y could be 0? No, right? If the x was on top, yeah, plug 0 in, you're good. So that's one thing I want you to notice. The second thing I want you to notice is it doesn't hit the y-axis. It gets very close to it, but it'll never cross it. And why is that the case? Well, if I hit the y-axis, is it x 0? And then guess what? That's undefined. No bueno. So what we do is we call the x and y-axis, okay, horizontal and vertical asymptotes. Okay? Now, this term we're going to see in a future lesson. I'm just introducing it to you now so that you heard it. So the asymptote just means it doesn't hit that line. Okay? It will never cross it. So it's like repellent, you know? It's like this line's coming in this direction and it gets close to it, but it's like, nah, they ain't crossing it. Okay, same thing with this one. Okay, this line comes down here, or this arc, I should say, and it'll get closer to the x-axis, but it'll never cross it. Okay, so we just call those asymptotes. And if you want, usually when you have an asymptote, you kind of do like a dotted line to indicate that it is. Because it's the x and y axes, you don't really do that, but I'll just emphasize it here, just so you can see it yourself. All right. So say where my notes go. There they are. Okay, and one final thing to put on here, and then we'll jump into it. Okay, other functions that share characteristics of a parent function are grouped as a family of functions. Okay, so just another little note there. So what does that mean? It means that if I were to transform, like let's say the square root function, I moved to the right or to the left or up or down, okay, that's one transformation. But I can do multiple. There's like an infinite amount of transformations I could do to that. So that whole group of those transformations is a family. Okay, this is a family of square root functions, is what it is. But the original, what it was before all those transformations, we call that a parent function. Okay? All right, here we go. Definition. Consider a function defined by y equals f of x. Let k represent a positive real number. The graph of y equals f of x plus k is the graph y equals f of x shifted k units upward. The graph of y equals f of x minus k is the graph of y equals f of x shifted k units downward. Wait, that's a k. There we go. All right. So we call these, sorry, I should have put that there, vertical and horizontal translations, which we said a lot of, like, I think we called them shifts. Last year I said, like, you're shifting the function, and that's fine too, but just know that translation and shift is being used in the same fashion, okay? Now, for it to be a vertical translation, the value has to be outside the function. That's what we're showing here in the definition, okay? So it's the function plus a number, the function minus a number. That's what's causing the vertical shift to occur, okay? So let's take a look at an example. Okay, so we're going to use the translations to graph the given functions. So part A. Again, it is critical when you're looking at this to know what the original looks like. Okay, so these are the originals, and they're just going to be changed. They're going to be moved or reflected or stretched and compressed, which we'll talk about a little bit later. So I'm just going to draw a generic graph, but when I draw the graph, I'm going to show the transformation specifically, okay? Make it a little bit better. So looking at the first board over there, I can see that the cubic root looks like that. But because the number is outside the function, okay, it's not underneath this root, it's outside the root, I know it's going to have a vertical translation. And because it's positive, it's going to move it up by 4. So 1, 2, 3, 4. Now what I'm going to do, I'm going to show what the original looks like underneath it. Now you don't have to do this unless you really want to. So there's the original. This is the cubic root of x. So me shifting it, that was bad. Let's try that again. There we go. That's a little better. Okay, it's just moving the entire thing. I'm just literally just taking it, moving up 4 units, and placing it back in its spot there. Now, could you plot additional points? Like, could you plug x values in and plot those points to make it more accurate? Absolutely. Okay, but in this example, all I'm trying to show you is what is the transformation that's occurring. Okay, now over here, it's hard to show both of them on the same graph. So 1 over x, we know looks like this. Okay, so there's 1 over x, right? And we know that it can't cross the x and y axes. Okay, so what's that -1 doing? Well, think about something for a second. That -1 is actually going to shift our asymptotes. It's going to shift where we're allowed to cross the axes, okay? So if I were to plug a 1 in, that would give me a 0, huh? So guess what? It can't cross the x-axis in this case. Okay, it couldn't in the other case, but in this case it can. There is a value that does make it 0. Okay, now for the bottom part, well, that's also going to change a little bit because now this is coming down. So what this is doing, let me see if I can mark it here. So the horizontal is shifting a little bit, okay? There's really no number here that's going to make me hit this line, but now I know I can hit the line at 1, okay? So this is going to come downward like this, hit 1, go a little bit past it, but again, it's never going to cross this line, okay? It's never going to, there's no values in here that's going to make it a -1. And then we already know what the other side's going to look like. Oops. There we go. It's going to follow that behavior where, again, it's not going to hit the asymptote where it's located, and it's going to continue in this direction, but not hit the y-axis, okay? So when it comes to reciprocal functions, what's on the outside of this is a vertical translation, and it's only going to move our asymptote. It's going to shift it down, our horizontal asymptote by 1 there. Okay? All right. Questions on that? All right. I would, I hate to erase the graphs, but I don't have a choice. I'm going to have to erase them. So that was the vertical. Now we're going to talk about horizontal. Okay. Same criteria. Consider a function defined by y equals f of x. Let h represent a positive real number. Okay, so here's what we got. The graph of y equals f of x minus h is the graph y equals f of x shifted to the right. Well, actually shifted, I'm going to use the variable here, shifted h units to the right. Okay? So the graph of y equals f of x minus h is the graph of f of x shifted h units to the right. Okay. The graph of y equals f of x plus h is the graph of y equals f of x shifted h units to of people always ask, like, why is it so opposite? Like, why is it the case? Honestly, what you can do with every function that follows this format, you can do an XY table and plot the points, and you'll see it's going to match that behavior. Okay, so it's not just like we mathematicians just say, hey, we want it to work that way. It just does when you plug the values in. Okay, so let's try an example. Same instructions. I'm not going to write the instructions again. We're just going to graph it. So we have g of x equals x minus 4 squared. And then for b, we have f of x equals 1 over x plus 3. By the way, your textbook does not do a lot of reciprocal functions like shifting and stuff, which doesn't mean that couldn't be like on a final or anything like that. So in my notes, I decided to give you some examples with reciprocal functions. That way you're not like wondering what's going on here. And this is going to benefit us in a future lesson because we're going to talk about these guys more in detail. So if you're looking in the textbook this week and you're like, why are those examples not like matching up? It's because I'm just adding them myself. The first one, so if I were to expand this, I know that's an x squared. That's a parabola. Parabolas, well, let's use this color. Look like this, okay? So that's what it looks like. That's the parent function. Now, because this is on the inside of the function, there's a horizontal movement. And because it's negative, we're going to move to the right, okay? So we're going to move 1, 2, 3, 4, and there we go. And again, why did I just do that? There we go. Okay, so yeah, there we go. 4 units to the right. Again, could you plot additional points to be more accurate? Absolutely. I do want to point this out to you though, okay? When it comes to a parabola, when you're moving things, their transformations, you're shifting the vertex of the parabola. That's what's happening here, okay? So anytime you're doing vertical or horizontal movements, you're just shifting where the vertex is going to be located. All right, reciprocal function. Let's see what this guy's going to do, okay? I already know what it looks like originally, but now at the +3, things are going to change again, okay? So first off, well, is there any way to make this 0? No, right? There's no x values that exist to make that 0. Okay, so it's not going to hit the x-axis. We know that already. However, okay, knowing what this is telling me it's going to be shifted, what, 3 units to the left? Okay. Do I want -3 to be included in here? No, that's where it becomes undefined. So guess what? That's where my vertical asymptote is. Okay, so let me just go ahead and shift it. 1, 2, 3. Okay, so my graph cannot cross that vertical line because if it does, you're telling me -3 can be plugged into here, and it can't. Okay, and then there's our graph. Okay, I should probably extend this so you can see it, that it won't touch that part of the graph. So when it comes to, if you want to categorize this, when it comes to horizontal translation with a reciprocal function, it's moving the vertical asymptote. When it comes to this guy, when it's a vertical translation, it's changing the horizontal asymptote of where it's located. All right. Questions? Awesome. Again, I just wanted to include these because those are really good. And they're fun looking graphs, right? I think they look fun. I like them. All right, we're doing good. So now we're going to talk about, well, the vertical and horizontal stretching and shrinking. Okay. So this is going to be vertical stretching and shrinking. I don't know why I don't like that word shrinking. I feel like we could come up with a better word for that, but let's define our conditions here. consider a function defined by y equals f of x. Let A, I'll put that there, the variable A represent a positive real number. All right, so here we go. If A is greater than 1, then the graph y equals A times f of x is the graph f of x, y equals f of x, stretched vertically by a factor of A. Just trying to outline, but that's not just the letter A, it's actually A in the context of a constant in this case. Okay? And vertical stretch, I mean like you're taking the function, you're literally like holding one end, hold the other end, and you're pulling it upward. Okay, you're stretching it up. If A is between 0 and 1, so I'm talking about a fraction here, then the graph y equals A f of x is the graph y equals f of x shrunk vertically. By a factor then. Okay? Yeah, so in other words, a fraction. Okay. So that's the vertical stretching and shrinking. Now we're going to talk about horizontal, okay? Tell you what, I'm going to put the horizontal over here, and then I'm going to put the examples there. That way we have this to look at as we're graphing it. So let's go with, this is vertical. Well, I guess I can't keep that in the title. Oh well. I think this stuff makes more sense with examples, so just hang in there. Once we get an example in, it makes it a little easier. Ooh, I forgot to write something down for you. Okay, this is still good. I got one final note to say. Sorry about that. It's me looking up and down with this paper. It gets a little hard. So here, note, any point any xy point on the graph, y equals f of x, the point x comma a y is on the graph y equals a f of x, okay? That's, you know what, it deserves a different color as well. We're gonna highlight that even more. So what that tells you is this. If you wanted to plot points when it came to transforming these, okay, whatever the a value is in front of the function, okay, if you want to plot a point equivalent to it, take your parent function point, let's say originally it was like 1, 2, it's now going to be 1 and then whatever a is times 2, okay, that would be the equivalent to it. So that's what's just telling you there. That's easy because we've done that in the past before. So that'll, again, it'll make more sense with an example. The horizontal stuff, that's where things usually get tricky, but I'll show you how to work with it. So if A is greater than 1, then the graph, now here's where it changes. So look where A was with the vertical stuff. It was outside the function. So for the horizontal, A is going to be inside the function. Okay? It kind of works with the translations, right? The vertical translations, it had to be outside the function for it to move up and down. The horizontal, it had to be inside the function. So this does follow that same pattern. Okay, so then the graph y equals f of ax is the graph y equals f of x shrunk horizontally. Okay, by a factor of 1 over a. Okay. Now let's talk about the fraction case. If a is between 0 and 1, then the graph y equals f of ax is the graph y equals f of x stretched, okay, vertically by a factor of 1 over a. Okay?
No horizontally.
Stretch, yes. Thank you. Thank you, thank you. Again, my eyes keep shifting here, so I appreciate that. Thank you. Okay, so let me just underline that part too. So again, if it's a fraction, and I think when I first approach these, I think of parabolas, you know, the U-shaped curves. So from a horizontal perspective, if your parabola is like really wide, right, okay, then you're taking both ends and you're stretching it horizontally is what you're doing, okay? So that's what this is telling you here. That's what it's visualizing. And just like that, I have another note to put here, and I'll give it a color as well. So note, any point x, y on the graph, y equals f of x, the point x over a y is on the graph y equals f of a x. Okay? So if you're plotting points when it comes to this guy, if you're plotting any xy points, okay, let's say the point was 1, 2 on the parent function. Okay, well now I'm transforming it by some a term. If you want to find the equivalent point, you're going to take whatever your a term is, divide the x coordinate by it, but the y coordinate is going to stay the same. Okay? Because again, you're stretching it horizontally. So the x value won't be, well, the y values won't be changing. It's just where the x is. What x term gets you that same y value? Okay. Again, let's just do an example. I think it's nice to have definitions, but at the same time, it's nice to have pictures next to definitions. So let's do that. Simple instruction, graph the functions. So just to let you guys know, I did 10, I think I did 10 lines there to just make my graph. Okay. Now, first what I would do is figure out what type of transformation is happening, right? So it's outside the function. It's not this. Let me clarify something. That would be inside the function, right? So that's where you're messing horizontally. But but this is outside the function. So we have a vertical transformation happening here, right? So if you look at what we have over on the definition side, it's outside and it's bigger than 1. So this is going to be stretched vertically, okay? And you can probably visualize in your head. So the normal parabola looks like this. That 2 is going to like squish it. Okay, it's pretty much taking those two things and it's just stretching like shoelaces. It's pulling them closer to the y-axis there. So we know already ahead of time like what it's going to look like, but let's just plot some points to make it as accurate as possible. So what I did is I just said, okay, let's just do -3, -2, -1, 0, 1, 2, and 3. And the good news is we know that parabolas are symmetric. So we're going to see some duplicate y values anyway, especially if we're going left and right of the vertex. My vertex is going to be here at 0 because it's not shifting anywhere, left or right. So plugging these values in, you get 18, 8, 2, 0, and then it just repeats on the other side. That's just the symmetric quality of it. So I guess we'll just say here, that's our vertex. So underneath it, let's just go ahead and say that we have a vertical stretch by a factor of 2. Okay. Now, plot points on here. I'm not going to be able to plot the 18 point. That's okay though. But what I will do is plot some of the other ones here. So -2 and 8 would be here. -1 and 2 would be here. And then we'll match on the other side. And boy, ain't that perfection? We need to come up, you use rulers for straight lines. We need like a device for parabolas, right? To make really cool parabolas. Just like a U-shaped looking ruler. Might be the next invention out there. If you do invent it, include me in there, okay? I can use some money. All right, part B. So given another graph, let's graph y equals f of 3x, okay? Now, for this one, it's a little bit different. The points I'm gonna use are -3, -3, 3, 2, and 6, -3, okay? I'm gonna plot them on this grid. And then we're gonna use these points to do the transformation, okay? Let's see, 1, 2, 3, 2, 6, there. Okay, so that's what it looks like. So now I'm not really giving you like an actual equation. I mean, you really couldn't call it absolute value because it ends. Absolute value would keep going on forever. You wouldn't have these endpoints, but just part of a function right there. Think of it like a piecewise function. Okay. So I'm going to draw transformation over here. So that's the original. I don't know if you want to put original underneath there, so that way you're not confused with it. Okay. Now, because it's inside, that 3 is inside, I don't even know what the equation is. They just gave me 3 points. So I'm just going to use the points to figure this out. But it's still inside of it. So there's some sort of horizontal transformation happening here. Okay? So looking at it, the number is bigger than 1. So I'm looking at this guy. Okay? So in this case, it's going to be shrunk horizontally. I really don't like that word shrunk. Remember the word compressed from last year? I said the word compressed. So if you say compressed, I'm okay with that. But yeah, the textbook says shrunk. I don't know. Just sounds weird. Okay. Now, what do I do to these points to figure it out? Well, look at the note I put on the bottom. Okay, so here's my points. So if I have a horizontal transformation happening, the point xy, which is this guy, is equivalent to x over a y. So what I'm going to do is I'm going to take my x terms and what? Just divide it by 3, right? That's all it wants me to do. So my new points, I'll put underneath it, okay? And I'll put this up here. So we're going to divide the x coordinates by 3, okay? So this will give us a -1, -3. next point would be a 1, 2, and then the last point would be 2, negative 3. Okay? Simple as that. So now I'm going to plot those points, and then we're going to just get a comparison here. If you want to plot it on the same graph, you can. If you want to just see it visually like that, but I'm going to plot it a little separately here. So negative 1, negative 3, 1, 2, and then 2, negative 3. There. Okay. All right. So you can kind of see, did it visually like just horizontally get compressed, right? It shrunk a little bit horizontally? Absolutely it did, okay? If you graph it and you get something that's bigger than that, then you're thinking, that's not good. It shouldn't be the case. Okay. Well, unfortunately, I gotta erase this. Okay. So let's try. Let's try reflections. We'll go on to that next. Okay, so we did one with a horizontal vertical transformation in terms of stretching and shrinking. Let's try reflections, and then we're going to put it all together to finish it. So we have the graph, y equals negative f of x. Okay, is the graph y equals f of x reflected across the x-axis? Now, let's go back to your geometry days, which was years ago. But let's pull up some of that knowledge. So if you remember, if it's a reflection across the x-axis, okay, that's where x stays the same, but the y-coordinate changes its sign, right? So that was the rule we talked about in geometry. We're doing the same thing here. I'm just using function notation to represent that guy. Now we have the graph y equals f of negative x. That is going to be the graph y equals f of x reflected across the y-axis. Okay, and again, just pulling from our geometry days, that means the y-coordinate doesn't change, but the x-coordinate does. The sign changes. Look. Okay, next one. Kaylee. Baby. Hopple wants to see you. Go to the media center. Something for Campfish. That's what she said. But yeah, it's just the x-coordinates changes, but y-coordinate stays the same. Example. So let's graph the line y equals negative f of x. Okay. Now, I'm not going to give us a function per se. I'm going to give us like the same type of situation over with 3 points. Okay. So the points, I'll put it over here. So the points we're going to be using is 1, 5, 2, 1, and 3, 3. Okay, so let me plot those on here. Okay, looks like that. Bunch of V's for these, isn't it? I mean, could you do more than 3 points and transform it? Absolutely, but obviously that's going to take a lot more work when you have more points, but the process doesn't change. Okay, because the negative's on the outside, that's following the rule for the x-axis reflection. Okay, so the x-axis reflection means keep x the same, but just change y. So underneath the the new points would be 1, -5. Okay, this one's gonna be 2, -1, and then this guy's gonna be 3, -3. Okay. And now we just plot them. Now, did you have to find the points ahead of time? Not necessarily. What you could have done, since you notice the x-axis, you can count the number of spaces to the x-axis. So this is 1 spot away, so the reflection, the image, is gonna be 1 spot away. So you could count the spaces as well. But either way, you have 2 methods to do that. And you can do the same thing for the y-axis reflection. You know, if I was reflecting this across the y-axis, I would just count the spaces to the y-axis and move it over. But if I want to, I can write the points ahead of time to see what it's gonna look like. So let me go ahead and finish this part. 2, 3, 4, 5, and 3, -3. There we go. I think the nice part with reflections is you can see, like, is it really a reflection? Does it truly match it up? And it does. Okay. Now, we have one last thing to do. And hey, we've got enough time for it. We're gonna do one final example where we put like all these together. Okay, so instead of just doing translations for one example, reflections for another, horizontal, vertical, shrinking, and stretching, we're gonna put it all together. There's one big problem. Okay, and I'm gonna give you, so here are some steps for graphing multiple transformations of functions. That way you don't make a mistake. Okay? So first thing you want to do, if there is any, horizontal translations. So move it horizontally if you need to. Next, do your horizontal and vertical stretches or shrinks. Again, that just sounds so weird. Okay, 3, reflections across the x and y axis. Was it the media center?
Yeah, I have to
Yeah.
go back.
Okay. And then the last thing, to finish the problem, do your vertical translation. Okay? So a nice order to make sure you don't mess anything up. Especially if you start reversing some of the orders of these things, you're not going to get the same picture that you want. Okay? And it's one of those things we do this intuitively when we actually start graphing these things. It's just nice to have an actual list here in case you get a function that's really complicated. It's like, okay, how should I even start graphing it? So for our example, we're going to plot this transformation. Okay, so -1/4, absolute value of x plus 2, and then a -1 there. Let's just write down the transformations first of what's happening. Okay, and I'm going to go left to right to figure these out. So for the negative that's on the outside, I know that's a reflection, okay, across the x-axis. Okay, so that's what the negatives tell me. All right, the 1/4, because it's on the outside of the function, that's a vertical transformation happening, and because it's between 0 and 1, okay, it's going to have a vertical shrink, which I'll put in parentheses. From last year we called it a compression. Okay, by a factor of 1/4. Next, inside of the function, we have a value, which means it's a horizontal shift happening. So this is going to have a horizontal, I'm just going to use the word shift, to the left 2 units, because it's a positive number. And then outside the function, we have a value. That means it's a vertical translation. So you're going to have a vertical shift 1 unit down. Okay? All right. Any questions on that? How I did that? And that's honestly, that's what I would do, just go left to right and list them. Now that we have these listed, now we can start using these steps to figure out what it's gonna look like. Here's what I would do in this situation, okay? And these problems that you'll be practicing have the situation for you. Pick some points, okay, of the original graph. The original graph's an absolute value, okay? So what you can do from the parent graph, let's go ahead and have these points. So -6, 8, 0, 0, and 6, 8, okay? So what I'm doing is I'm just plotting just generic points, and then I'm gonna use these transformations against the points, and then I have a final picture in the end. I like to do a side by side. Let me put this over here. Okay. All right. So, oh wait, 8s. What am I doing? That's -8. I was looking at that, I'm like, those should be the same numbers. My bad, guys. I'm sorry about that. Knew that looked weird at first. Okay, so these points come from the original graph. Absolute value of x, okay? So, let's do this. First, okay, let's talk about horizontal. So, if I am, was it +2? Okay, so if I'm shifting it to the left 2, okay, my points are gonna be where? What are my x coordinates gonna be now if I'm moving it to the left 2? So if it was -8, 8, it's now gonna be -10, 8, right? You're just moving it over to the left, 2 more. Okay, so we have -10, 8. And then we'll do the same thing. This would be -2, 0. And then that guy would be a 6 and an 8. Yeah, sorry. When I was first writing, I was writing down the units already shifted when I first did the original. Okay, so we took care of the horizontal. Now, number 2 says take care of the horizontal and vertical stretch or shrink or compression. Okay, now because it's on the outside, do I have the note here? Oh, I deleted the note. You're going to take the 1/4, okay, and you're going to multiply what? The last value, the y values, by that 1/4. So I'm -10, 2 now. -10, still 0. 1/4 times 0 is 0. And then the last one's going to be 6, 2. Okay? Now, could you draw a graph each and every time doing this? Yes. And I did that in my notes. Don't do that. I mean, it's a good visual, but it's just easier to work with the points and then graph the final result. Okay. Next, third step, apply the reflection. It's a reflection across the x-axis.
Can I please have Josh Steele, Adam Exline, Zane Elick, Ashton Baker, and Mikey Jerushol down to the media center right now? Thank you.
I have so many words to say, but I'm on camera. I can't say those words right now. Okay. So anyway, reflection across the x-axis, that's when we just change the y coordinates, change the signs of them. And then the fourth step is the vertical translation. So if it's going to move down 1, what coordinates are going to change here then? The y. So this is now going to be -10, -3, -2, -1, and then the last one's 6, -3. So these are my final points, and those are the points I'm going to use to graph it. Okay? I'm going 10. Wow. 1, 2, 3. Okay. So here we go. So we have here -10, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. So there's that point. -2, -1, and then 6. 1, 2, 3, 4, 5, 6 down 3. There we go. I'm trying to make these points a little bigger. So there's my transformation. So originally the function looked like this, right? That's what the parent function was. But then, after applying these transformations, it now looks like this, okay? So I would behoove you to do that. Like, pick a couple points, including the vertex of this absolute value, and then go through these transformations and then plot your points at the end. Okay? All right. That is transformations. Good to go.